Professor, you're still muted. We can't hear you.
Can you hear me now?
Yeah.
Thank you for letting me know. Now, so the example we've done before, okay, is what we call, like this example, is what we call centric symmetrical bending. Okay, so I'm going to show you what's the difference with the other one. Okay, so the example that we've done, okay, so the example one, okay, is known as centric symmetrical bending. Okay, so what do we mean by centric symmetrical bending? Okay, so if it's centric symmetrical bending, okay, the formula that we apply is usually, so the formula is usually stress x is equal to minus mz over izz multiplied by y. Okay, so that's the formula. But by looking at this formula, what does this actually means? Okay, so now symmetrical bending has nothing to do. Okay, wait. Before I go on, now let me ask you a question. So if we have a structure loaded this way, okay, so we have a simply supported distributed load and a P. Okay, so this is one of loading system. Then I have another beam. Okay. Okay. So if you look at the beam on, so this is condition number one. Condition number two. Can anyone tell me which one will be generating a centric symmetrical bending? Condition one or two? Anyone, please?
Two.
Two. Anyone
This is
else?
a trick question, actually. It's probably both.
Huh?
Is it a trick question and it's both?
Yeah, so you're absolutely right, okay? So whether is it symmetrical or unsymmetrical, okay? But both are centric, okay? Either symmetrical or unsymmetrical has nothing to do, okay, with how the structure is loaded in terms of geometry, okay? At this point of view, in the, okay, if I draw a transformation, okay, x and y, okay? So this is also x and y. So based on this plane, right, you cannot tell whether is it symmetrical or unsymmetrical, okay? You have to view at a cross-sectional. So now if we were to look at a cross-sectional view, okay, so this has nothing to do with condition one or two, but I'm going to draw a different cross-sectional view, okay? So right, sorry, I have to draw it wait. Okay, so I'm going to draw. Okay, so this is one cross section. Okay, then we have another one. Okay. Right. Then all of them. So if I were to draw our axis, this is Y, this is Z, rotation about X, and it's the same. Okay. So if I'm going to label this as our centroid. Okay. So this position, this is our centroid. Okay. And this is just arbitrary. Okay. This is our center. In fact, it should not be there. My apologies. It should be slightly higher. Now, can anyone tell me which one is symmetrical bending? Anyone? The left or the right one? Anyone will want to make, is it the T or the N? Is it the T or the N will have symmetry? And I'll give you another condition, okay? The moment, okay, moment is applied about the z-axis. Okay, so both of them moment applied about the z-axis. Okay, so which one is symmetrical loading? Anyone?
Is it both again?
Yeah,
the cross section.
it is. It is. Matthew, you are making a guess based on intuition. Yeah. Okay, let me show you what does it actually mean by symmetrical loading. Okay, let me show you. Okay, so we're going to label this as alpha, beta, I, and point J. Again, alpha, beta, I, and point J. Okay, so if we were to look at the formula, all right, so if we look, we now look at the formula. Okay, so if we were to look at our formula that states that stress X is equal to minus mz over IZZ Y. Okay, so both of them, I do apologize, both of them use the same formula. Okay, both of them use the same word. Stress X is equal to minus mz over IZZ multiplied by Y. And this one is also m stress z equal minus mz over IZZ multiplied by Y. Now, what is the constant, right, for this, regardless of whether is it alpha, beta, I, or J? Okay, I'm going to write here for both cases, regardless, right, regardless of position, right, mz and IZZ are constant, right? Regardless, right? MZ and IZZ are what? Constant, right? So what is changing is when alpha point alpha and point beta, comma, y is the same. For both cases, yes or no? So y is this distance from here to here, from the centroid. That's our y, right? And also, for point I and point J, y is the same, right? So based on this, what we know that stress X for point alpha, okay, so stress X for point alpha is equal to stress X for point beta. And stress X for point I is equal to stress X for point J, right? Because alpha and beta have the same Y value. I and J also have the same Y value, yes or no? Regardless whether positive or negative, right? I and J, you have Y over here, right? That Y is the same, okay? So when this condition is met, okay? When this condition is met, right? The structure is under symmetrical loading. Okay, so symmetrical loading is based on what? Based on stress. The symmetrical is not based on what? How is it loaded? I mean, how is it loaded has a point, okay? It has, how is it loaded has to be, it only has to be loaded in one axis only. Like what I say, moment is applied about the z-axis only, right? So that's why we can apply this formula for both cases. What is changing is the y. So for this case is what we call symmetrical bending. Okay, now for symmetrical bending, oh sorry, not just symmetrical, for centric symmetrical bending, okay, the position of the centroid, okay, is the same as the neutral axis. Okay, symmetrical, centric symmetrical loading, the position of the centroid is the same as the what? Neutral axis. Okay, so to determine the centroid, this is all based on what? Geometry. Okay, to determine the centroid is just based on geometry. The neutral axis, it means what? Neutral axis means stress X is equal to what? 0. So what do we mean by stress X is equal to 0? Okay, so we have not spoken about the neutral axis. I think you guys have the impression of a neutral axis. Okay, so now if again we have a cross-section area. Okay, so this is our cross-section, right? So this, if I were to draw a transformation, so this is point Y, point Z, rotation about X, okay? And this position over here, right? This is our centroid. So because it's rectangular, it's obvious, okay? The center, where the top half and the bottom half have the same cross-sectional area in terms of size, that's the position of centroid. Now, if we were to assume that any